In this last lesson, which is lesson 4 for this chapter, we're going to have a bit more of an extended look at some of these problems. The first thing I actually want you to do is just have a go at some problems which put together all the things that we've done so far in this chapter. So if you have a look at 7e, I would recommend picking out the questions marked E/P, which is the exam style questions. And you're welcome to do any other ones from that exercise as well, but they're all good practice of just all of the things that we've done so far. And then what we're going to go on to is look at connected particles, so things like pulleys and so on. So before we do anything more complicated with friction and so on, I just wanted to look at a bit of a recap about how we deal with connected particles. So I want to find the acceleration and the tension in these two scenarios involving pulleys. So the first one, we've just got a vertical pulley here. We've just got a mass of 4 kilograms and a mass of 3 kilograms. The forces are obviously 3G and 4G. And we've also got the tension. In terms of what's going to happen, well, this one is heavier than this one, so it's going to accelerate that way, and this one's going to go upwards at a rate of A. Now to solve the equation, I'm just going to call this particle P, this particle Q. We've got to form an equation of motion for both of these particles. So for object P, I'm going to resolve downwards because it will accelerate downwards. So I can write 4G minus T equals 4A. For object Q, that's going to accelerate upwards. So I can write T minus 3G equals 3A. And now I can solve these equations simultaneously to find T and A. So I'm going to add them together first of all. So that would give me 1G equals 7A. So A is G over 7, or 9.8 over 7, which is 1.4. You can then find the tension from that. So you can put it back into this equation here. So that gives me T equals 33.6. So that's how we do it there. So we write an equation of motion for each particle. And whenever we've got connected particles, so things with pulleys, that's generally the approach, is write an equation for each particle. Let's have a look at this example here. So we've got a pulley on a table, and we've also got some friction on the table. So we're going to do the same as before. We're going to label the forces involved. So I've got a weight of 5G with a tension here holding it up. We've also got the tension in the string pulling this one along. It's got a weight of 2G. It's got a normal reaction force of R. And there's presumably going to be some friction trying to stop it. And here, the particle, this one's going to move down, and this one is going to move to the right. We're going to try and find T and A, exactly the same as we did before. So here I'm going to call this one object P, this one object Q. So for P, resolving to the right, we have got T minus the friction equals 2A. Now I've got to work out the friction. Remember, friction is mu r. So it's going to be T minus 0.2 times the reaction force R. Well, that's just going to be 2G. It's quite a simple case. There's no other forces affecting it vertically. So that's just 2G for R. So I can solve this to find, oh no, I can't solve that quite yet. I need to do it for Q as well. So for Q, we can resolve downwards, and we can say that 5G minus T equals 5A. Okay, so I've got these two equations here. I'm going to add them together to eliminate T. So I've got 5G at minus 0.4G. So that's 4.6G equals 7A. So I can find out what A is. So 6.44 meters per second squared. And I can find t by substituting it into either of those equations. So it's 16.8 newtons. Okay, so the strategy is still the same. Write an equation for both particles, but you might have to do something with some friction or something like that in there, but we now know how to do that. Okay, let's have a look at this example here. So one end of a light inextensible string is attached to block A, that we can see in the picture, mass 2. It's held at rest on a smooth fixed plane. The fact that it's smooth, that makes things easier because we do not have to worry about friction here. And it's inclined at an angle of 30. What else do we need to know? It's attached to a block of 5 kilograms. It's released from rest. Show that the acceleration is 4/7 g. Okay, so we're going to do exactly the same as what we do normally. Put all the forces on. So this is 5g. This is t. This is t. Put our weight on here. 2g. That's 30. So this is 2g cos 30. And 2g sine 30. There's no friction, but we are still going to have the reaction force there. So here the reaction force will just be 2g cos 30. But we probably don't need that because we don't need to work out friction here. In terms of the direction that it's going to accelerate, if this is smooth, then I think it's pretty safe to assume that it's going to accelerate like that. So same idea as we did before. Let's do an equation for each object. So for object A, it is accelerating up the plane. So that's going to be t minus 2g sine 30. That's the force that's trying to stop it, equals 2a. For object B, going to resolve downwards, so that'll be 5g minus t equals 5a. And now I've just got to solve these simultaneously. So I'm going to add them together to eliminate t. So that's going to be 5g and then minus, well, 2 sine 30, that's just 1. So it's going to be 4g equals 7a. So a is 4/7 g. And that's what it asks us to show. Find the tension in the string. So I'm going to substitute into this equation here. So I've got 5g minus t equals 5 times 4/7 g. So we can either write that as 15 over 7 g, or as a number that is 21 newtons. There we go. State how you've used the fact that the string is inextensible in your calculations. So inextensible, this means that the acceleration in both parts is the same. Okay, so the acceleration is equal on both sides of the pulley. Now for this last part of the question, we want to find the magnitude of the force exerted on the pulley by the string. So whenever we've got a tension in a string here, there's also always an equal and opposite force on the pulley in the other direction on the string. And we talked about this when we studied it before. Imagine if you were like holding onto 2 bags of shopping, you're going to feel a force on you. That's basically what the force on the pulley is feeling. Now I'm going to zoom in just on this kind of bit of the diagram here and redraw it. So here's the slope. Here's kind of the back of the slope. And then at the top we have this pulley. Now we've got a force down this way of t and a force down this way of t. The total force on the pulley, or the resultant force on the pulley, is going to be in this direction here. It's going to be just down the middle. It's going to basically split them in half. Because these are both the same value, it's not going to pull more in one direction than the other. It's just going to go halfway. Now remember, in this slope, the angle down here was 30. So that means that this big angle here would be 60, just because this is a right angle, and angles in a triangle sum to 180. So if we split that in half, then this little bit here must be 30. Okay. And what we want to try and find is what is this R force here. Now, to turn this into a triangle that I can actually analyze, I'm going to make T the hypotenuse. So I'm going to do this, where that's a right angle. So I've got this triangle here. Okay, because when we're trying to split a force up into its two components, we want the real force to be the hypotenuse. So I'm just going to draw that triangle out now. So it's a right angle down here. This is T, which we worked out earlier was 21. This angle is 30. And then this is R. So looking at that, I've got the hypotenuse and I want the adjacent. So it's going to be 21 cos 30. It's going to be R. So 21 cos 30, let's just work that out. 21 root 3 over 2. However, there's also another one of these triangles on this side, okay, which is contributed from this T. So the force on the pulley is actually going to be twice this. So it's going to be 21 root 3 newtons would be the force on the pulley. Okay. Let's have a look at another example. So here we've got similar kind of setup. We've got a slope with two particles. This time we have got a rough inclined plane. Okay, so that makes things a little bit more complicated. We've got to take friction into account. It's just basically describing the diagram for most of it. Okay, tan alpha is 0.75, or tan alpha is 3/4. We've dealt with that lots of times. So tan opposite over adjacent is 3/4, so that means that's 5. Sine alpha is then opposite over hypotenuse, and cos alpha is adjacent over hypotenuse. The coefficient of friction is 0.2. So let's write that somewhere. Let's just write mu equals 0.2. And we've got to find the acceleration of the system. So I'm going to assume that it's going to do this. It might not, but I'm going to start by assuming that it moves in that kind of direction. Let's put the forces on. So we've got 10g. This is T. T here. There's going to be some friction going down here. Put the weight on. Resolve the weight. Should put R on as well. Okay, I think that's all my forces. Quite a few on this one. So the first thing to do is probably to work out friction. Whenever we've got friction involved, it's always a good idea to try and work that out first, or at least get an expression for it. So we need to resolve just for particle P and perpendicular to the slope. So that's going to give me R equals 5g cos alpha. Or I could write it as 5g times 4/5. So 5 times 9.8 times 4/5. So that gives me 39.2. And now I can write an equation for P going parallel to the slope and up it, because I've now got R, which I can use in mu R. So I've got T is pulling it up, minus the friction, so that's minus 0.2 times 39.2, so that's mu R, and also minus the weight pulling it down, so that's 5g sine alpha. And that equals ma, so that's 5 times a. Let's work out any numbery bits that I can just to simplify this. That's T, we've got 0.2 times 39.2, and minus 5 times 9.8 times sine alpha, and sine alpha was 3/5. So you can actually rewrite this as t minus 37.24 equals 5a. It's a bit simpler. Let's do the same sort of thing for object q. For q, we're just going to resolve downwards. So we've got 10g minus t equals 10a. And now we can solve these two equations. So I'm going to add them together to eliminate t. And then find out what a is. So I get a is 4.05 meters per second squared. And then to find t, I'm just going to put it back into this equation here. So t is 57.5 newtons. Okay. So again, the algebra involved in the solving is not very complicated because all of your working is on here on the diagram. That's the important bit. Okay. So you should now be able to have a go exercise 7F, which is similar questions to this. We've done one of them there. Basically involving pulleys and slopes and putting everything together. And these questions are these would definitely be classed as quite tricky questions in an exam if they came up. Later on in the course, there's a few exercises we haven't done in chapter 7, but that's because we've got a few other things we need to study before we do them. So exercise 7D we haven't done, but we need to come back and do that one once we've done moments, which we'll do later on, just because I like to teach in a different order. And also mixed exercise 7, that's obviously got some questions that involve moments, which we haven't studied yet, but there'll be good revision when we come to the end of the course.